Yeah, thank you, Paul. Also, thanks to all the organizers for great workshop and the opportunity to share some of my research. So today I'll be talking about both some development and applications I've done around VMC as a tool for studying excited states. And first part of this will be on my sort of graduate work when I was at Berkeley with Eric Newsman's group studying molecules. And then towards the end, I'll share some of the extensions I've been pursuing in this line in solids in Chicago. So to first just sort of broadly motivate like excited states and their importance, that they play a key role in a lot of different phenomena and applications. I'm just pulling some examples from the literature. For example, they're important in photophysics of DNA related to DNA degradation and emergence of cancer. They play a role in catalytic processes, for instance, the use of nanoparticles in that role. And something I'll come back to towards the end is the potential use of the excited states of point defects in solids as qubits for quantum information purposes. But from the standpoint of theory, I think one of the sort of challenges when it comes to modeling excited states is that they really come in a number of different types, that if you even consider only this collection of fairly small, simple molecules that I'll be showing results for later, you can have a number of different classes of excited states, things that are maybe sort of most familiar, like single excitations of your valence electrons, but there are more challenging categories like doubly excited states, your dominant configurations as if you've got two electrons excited. You can have cases where the excited state is associated with the movement of charge in real space, like charge transfer, and then also possibilities like exciting among your core electrons instead of the valence. And in the electronic structure community, of course, there have been a lot of methods like to tackle excited states, like TD-DFT is probably the most common right now, but there are also various methods on the wave function side of theory, like coupled cluster theory and equation of motion. There's multi-reference perturbation theory approaches like CASPD2. These are often sort of state average. And then there are approaches like a sort of basically efficient brute force like selected CI or DMRG. But a lot of these methods often have sort of corresponding like challenging categories when it comes to excited states. Like it's known TD-DFT can have trouble with doubly excited states or charge transfer. I'll be showing results later of examples of large excitation energy errors when it comes to coupled cluster theory for doubly excited states. In the cases like charge transfer, often having a state average formulation like you have in CASPD2 can limit you because the appropriate orbital shape should be relaxed for the excited state with the movement of charge. And then there's still issues with scalability for things like selected CI. So like you could have a sort of like wish list of like a method that would be broadly applicable across different categories of excited states in terms of desiring like good treatment of more configurational characters, strong correlation effects, pairing that with also weak correlation treatment and doing that in a balanced way for ground and excited state, plus things like orbital relaxations and an ability to scale to larger systems. And I think there are a lot of features of VMC that sort of position it to play this role rather well for excited states. There's been a lot of development on different approaches within a VMC framework, but everything I'll be sharing is based around this particular objective function, capital omega, that the Newsman group at Berkeley developed, where instead of like the traditional ground state energy minimization, you normally have, you're minimizing this sort of objective function to target the state that's directly above this input parameter little omega in energy. And this sort of quantity, a sort of detail is like it is really related to the variance that you in practice, you self-consistently vary this input energy little omega to the energy of the state that you're targeting minus standard deviation of that energy. And this turns the capital omega into the variance. So the variance, of course, has a minimum of 0 at any, if you had any exact eigenstate, but doing it in this manner allows you to have a state-specific treatment tailored to your state of interest. And I'll show examples of like how this sort of approach within VMC is pretty useful, I think, for sort of cross-validating more traditional quantum chemistry approaches for excited states. But it is something that needs effective wave function ansatzes and also good optimization algorithms for minimizing this objective function. So first, just a note on wave functions. Everything I'll be showing here is based on multi-Slater-Jastrow wave functions, so some set of determinants. And a note here is that I am like drawing these I am exploiting like all of the improvements that have been made in selected CI as a good way of efficiently identifying the most important determinants and getting those strong correlation effects. Those get paired with a Jastrow factor. I've worked mostly just at the 1 and 2 body level. And of course, this sort of framework allows systematic improvability with more determinants and higher body Jastrows. Now, when it comes to the wave function optimization, this is where a lot of my personal method development work has been, that there are a number of just plain numerical algorithms that you have as options for finding the best parameters for your ansatzes. Sort of what's been most common in QMC and also QMCPACK, the code, has been the linear method, where you're constructing this sort of generalized eigenvalue problem. These matrices H and S are built out of basically wave function parameter derivatives, and solving this for your eigenvector C will be your update vector in parameter space, getting you to a better set of parameters for your wave function. But one thing I explored in my graduate work was the possibility of using these methods of accelerated descent that come from the machine learning world, and have had a lot of success there. There are different flavors of this, but sort of generically, you can all think of them as trying to retain some sort of memory of previous values of your parameter gradients from earlier steps of your optimization of the wave function. And one sort of finding in previous work I first did in the ground state and then extended to excited state optimization is that often you can have very effective optimization through hybrid combinations of these two classes of methods, the linear method and descent. And so these sort of algorithms are present within the code, QMCPACK. But like the sort of like big picture among the algorithms is like with the linear method and descent, that you have sort of trade-offs in terms of things like the number of parameters you can effectively handle. The linear method traditionally has often been below about 10,000 wave function parameters, whereas descent methods are somewhat more scalable. But there are issues like the linear method's more second order nature allows it to get closer to the vicinity of the minimum compared to a lot of the descent methods. But the bottom line is that I think you can often have the best of both worlds through a sort of hybrid approach in terms of scalability and more flexible and accurate ansatzes while retaining like good convergence and computational cost. So in terms of now showing some applications of all this sort of machinery, like the sort of initial tests can be on sort of single excitations in fairly small molecules. So these are things that have been benchmarked elsewhere in the community very well with selected CI here in the blue in these plots. Couple cluster theory in the purple and the red can be extremely accurate for these sorts of systems, but you can also do fairly well with VMC within about 1/10 of an EV or better accuracy in doing this with what are still fairly modest wave function ansatzes of a few hundred determinants. So you don't need like truly exhaustive variational treatment of the correlation to get good excitation energies. So this is like the sort of first reassuring check on its accuracy in molecules. But if you look at sort of more challenging categories of excited states like double excitations, these are a situation where you can get good answers from selected CI, but with couple cluster theory, even if you go to the expense of full triples in the purple, you can still be off by half an EV or so in your excitation energy. And it's even worse with more approximate forms of couple cluster. In contrast, the multi-reference quantum chemistry approaches like CASPD2 are quite successful here. That accuracy we share with the VMC framework. Now, if you just go slightly larger in molecular size, say up to hexatriene and benzene, you're already at a level where things are generally too large for really exhaustive benchmarks from selected CI on any big energies. And what you have instead are this sort of range of answers from different levels of couple cluster theory and different types of multi-reference perturbation theory. So I think these are the sort of situations where I think it's most useful to come in from another direction with VMC and see which methods are supported. So in this case, with the hexatriene case, this doubly excited state, in fact, has a fair amount of singles character mixed in that, and VMC agrees well with couple cluster. And then we can also make comparisons over a fairly wide spread in predictions to the different multi-reference perturbation theories for the benzene example. In this next category of excited states with charge transfer, this ammonia fluorine case and this benzonitrile example, like the situation is kind of reversed from what we just saw with double excitations. It's now couple cluster theory with augmented basis sets that's the most accurate and also in best agreement with VMC, while in contrast, CASPD2 in green and yellow on the left and red on the right has, again, some errors of multiple tenths of an EV, like often due to like the sort of limitations of state averaging when you've got these sorts of charge transfer cases. And the sort of largest example from this sort of molecular study I did as a grad student is this case with uracil. It's a sort of similar story in terms of, in the literature, having a range of different predictions from coupled cluster and CASPD2, but VMC sort of best supported the generally higher excitation energy predictions of coupled cluster compared to somewhat lower values for CASPD2. But the sort of message from the molecular work I found in my PhD was that across these different categories of excited states, this sort of VMC machinery can be kind of consistently accurate in a way that's not really true for things like coupled cluster or CASPD2, which might be great on a certain category of excited state, but then have more problems elsewhere. And so that sort of success with molecules sort of motivated what I'm pursuing now at Chicago, looking at the excited states of point defects in solids. So to just motivate this again a bit more, that things like the NV center and diamond or other defect examples I show have a lot of potential for nanoscale sensing applications or quantum computing, but there's still a lot of need for like good first principles calculations to try to identify like sort of best host material and defect combinations you'd want for applications. And what's sort of like available elsewhere in the community are like different approaches based on DFT or GW, and also now more recently and importantly, I think different quantum embedding techniques, which have a range of sort of different strategies depending on like what sort of quantity is at the heart of the embedding methodology. But already in what that community has been doing, like you run into situations sort of similar to what in spirit to what I was showing with molecules, that in this sort of recent study on a silicon vacancy defect in diamond, what's shown on the left are these different embedding approaches, and for different excited states, depending on the state, you may have considerable ranges in excitation energy predictions and are often in a situation where there's relatively little experimental guidance. And so this is where things like VMC or QMC in general, I think, play an important role as systematically improvable, like high accuracy approaches. And so my like first initial sort of test system for this was the carbon vacancy in diamond. So you're taking just 15 carbons, leaving one carbon atom. There is some work on excited states previously in the literature, like a delta SCF approach based on DFT, and also a diffusion Monte Carlo study with pretty minimal trial wave functions, now about 20 years old, that provided some excitation energies in this system. So, but the sort of encouraging initial tests with like all of the sort of VMC machinery that I've worked with and found for the supercells I'm able to do, I can get within the range of excitation energy predictions is sort of established from the literature. And that can still be done with still relatively modest wave function expansions, like a few hundred to up to maybe about 1,000 determinants in some cases. So that was the sort of like initial check on the accuracy of this VMC approach now for defects. And then I looked at this silicon vacancy example that I showed a moment ago, specifically these particular singlet excitation states that are pretty localized. We've been studied with different types of embedding methodology, this density matrix embedding theory, and also what's known as quantum defect embedding theory, sort of Green's function GW-based approach that groups I'm working with at Chicago have been recently developing and applying. There's also been a very recent study also at Chicago on TDDFT with different choices of functionals for these defect states. But you can see situations where these methods certainly don't all agree on excitation energy predictions. And the finding from my VMC work on this is best supported the predictions in excitation energies from the quantum defect embedding theory and TDDFT with a particular choice of hybrid functional. So these sorts of more intermediate excitation energies of, say on the right, of about 0.6 of an EV compared to somewhat higher predictions that come from the density matrix embedding theory. So like these sort of results I've been working on the past year or so, or like trying to build up some examples of VMC as a tool that you can sort of broadly deploy in this way across different defect excited states. So to sort of wrap up and give some like closing thoughts, like I hope like some of like the results I showed indicate like VMC as some sort of general purpose promise for excited states in molecules being pretty accurate, regardless of the type of excited state that you looked at, and also now extending this for point defects in solids. But it's still a relatively new approach, I think. And so like I think there are a lot of opportunities for like wider application to get a better sense of its accuracy. And like this, its success so far has of course relied on like having good wave function ansatz and some of the fundamental algorithmic work that I developed, but it's still always, I think, better to find better, more efficient ways of doing the VMC optimization and also making it more user-friendly. It is also an important effort. And I'll just sort of close mentioning that like the sort of recent work I've been doing with defects in solids makes me think that I think there are a lot of opportunities at like the confluence of QMC and the many quantum embedding approaches that are proliferating now, like comparisons on defects in terms of benchmarking excitation energies, but I think also methodological opportunities, perhaps of QMC is the sort of like high-level approach between various within various quantum embedding schemes. I think could open up a lot of interesting applications and studies. But with that, I'll close first acknowledging my advisor for my PhD, Eric Nuskman, who provided a lot of very great mentorship in the initial hybrid algorithm development work and also the applications to molecules. Also want to thank my advisors now at UChicago, Laura Gagliardi and Julia Galli, with the ongoing project with defects. I'm supported by a postdoc fellowship out of the Chicago Center for Theoretical Chemistry, and also want to acknowledge various computing resources. Thank you.
Thanks very much, Leon, for an interesting talk, interesting work. Open for questions. All right, well, I certainly have a question, and this is sort of a question about convergence, which I imagine you're still studying. So we know just tackling ground states of solid, doing finite size extrapolation can be a challenge for a lot of systems. Defects add to that, and then also now you're looking at excited states. Well, one's also worrying more about converting the quality of the wave function, in addition to, getting the tails of the excited state orbitals and so on. So what is your experience so far as regards, getting good converged quantities?
Yeah, so there's, as you say, like, I guess sort of like different dimensions in terms of the convergence. Maybe, I guess, to start with the wave function convergence aspect in terms of optimization, that it is something, I guess the key considerations are basically like complexity of the wave function you're trying to optimize and the algorithm that you're using. That with what I was showing with like multi-determinant wave functions of like say a few hundred up to about 1,000 or so determinants and 1 and 2 body Jastras, I feel aren't necessarily too difficult to converge with the wave function optimization, like especially with the sort of like hybrid approach that you do need to like do it carefully and check, but it's usually not too painful. Going to things like adding orbital optimizations, things like I've studied more in molecules can certainly be more painful. Certainly with, I guess, in the solid state with the sort of issues of supercells, I think probably, at least with the resources I have available, going up to about the 64 atom, 250 electron scale is, I think, what's mostly feasible, certainly at a level that's deployable across like multiple systems to get multiple results. I am also, I should point out, like benefiting from trying to, from the fact that I'm pursuing excitation energy differences instead of like absolute energies, that it's more about having balanced treatments that like are still converged at some level of like wave function quality for the ground and excited state, and then having a good difference. But they're both individual calculations are still far from like having absolute answers on each one.
So much, Mika.
So very interesting work. So when you're doing the expansion in this localized theory, then you can, the determinants are coming for VMC from this localized embedding theory, or is it the overall, you do different things? How do you fit the determinants for the?
Yeah, so the determinant generation comes from basically unconverged selected CI. So you can still take the whole system and some subset of the orbitals, correlate the electrons within it, but you aren't after like exhaustive treatment with the selected CI. It's just meant as an efficient way of generating, say, a few million determinants, which is still very small, of course, compared to the whole space. But with that few million, you can be reasonably confident your first few hundred to few thousand are like a good initial guess. And this then gets further re-optimized in the presence of the JASTRO at the VMC.
But the embedded theory only has the embedded excitations from the center itself. So those are the same.
So like the embedded theories, like I'm comparing to, like have like their own methodology. Like the VMC results are just treating like this entire supercell.
Yeah, that's the thing. So if you could just if you couple it together, it'd be great. So make it even.
Yeah. Certainly, like I think in scalability to like larger system sizes, trying to couple within like the QMC within an embedding framework could be a very interesting direction.
Oh, all right. Now I'll just ask if anyone online has a question, and they should just unmute and ask. I did check to see if there was any hands just now. Whilst I pick out a quick question in the room, I don't hear anyone unmuting, so we'll go to Jaren.
Yes, we've got one question. So in a system like one you're showing, like if you went to a system where, say, the wave functions could improve a lot in the bulk, just by from the wave function you begin with, would you anticipate challenges there? Because I'm thinking as you go to a larger system, that as you make excitations, a lot of those things that you're promoting will actually just get absorbed into the bulk in terms of the improvements to the wave function, maybe even the excited state. Would that cause a challenge? Would you need a filtering method? Or does this work particularly well because in the bulk, the wave function is already pretty well described by default?
I suppose, yeah, if you had a situation where the bulk, I guess, really matters, and you are expecting, say, like substantial changes and improvements in the wave function as you optimize, yeah, related to the bulk, like this, I think could be more challenging, certainly like in terms of demanding like what larger wave function expansions, like harder optimization, everything there, like the excited states I'm considering with the defects, these are like highly localized, like the relevant configurations are all showing like excitations within orbitals localized around the defect, and the bulk is not playing such an important role in that sense. And because I'm also pursuing just excitation energy differences and just needing a good balance between ground and excited state, I think that saves me a lot in terms of being able to get away with like much more modest wave functions.
All right, let's thank Leon for venturing to talk.